This is lecture 14 for Chem 223. Today we'll be talking about spectrophotometry, which involves rainbows but not unicorns. Okay, spectrophotometry is the study of how light interacts with matter. So just to give you a brief description of how light interacts with matter, if you shine different wavelengths of light onto matter, it will cause different results. So if you shine microwave radiation onto matter, you generally excite the molecules to rotate. So when you put food in the microwave, you're generally causing molecules to rotate. And then, of course, they rotate and bump into each other and transmit their heat that they're gaining from that rotation into other translational modes. But usually when you put food in microwaves, the thing that absorbs the most microwave radiation is water. Water absorbs radiation, especially microwave radiation, really well. And so next time you're making a bowl of oatmeal, really you're just spinning up all your water. And if we look at the infrared spectrum or infrared region of the electromagnetic spectrum, light in this region tends to excite vibrations in molecules. So if any of you have taken organic chemistry lab yet, and looked at all your IR spectra with the OH stretches and the CO stretches, etc., that's what we're looking at here. For this class, we're mostly going to focus on ultraviolet and visible light interacting with matter. So this region we generally shorthand to the UV vis. So we call this the UV vis region of the electromagnetic spectrum. And light in the UV vis region generally induces electronic transitions in atoms and molecules. That means it excites electrons from lower energy orbitals to higher energy orbitals. And this is what actually causes a lot of your colors. So the color on my shirt is just caused by transitions of molecules that are occurring as light is hitting those molecules. Right, so to give you a little bit better idea of what's going on here, or to give you just an example of a real-life application of this, we're going to talk about how a street light works. So street lights are generally sodium lamps, and they've got a couple other types, but we're just going to talk about sodium lamps today. And what sodium is a metal, but it's a resistive metal. So if you have flow electrons through it, it causes it to heat up. And so some of that heat that you're giving to your sodium atoms gets imparted to the electrons in the sodium atoms. So now we're not talking about the electrons that are flowing through the sodium, but the electrons that are already there. Those electrons can get excited to higher energy states. And then once they're in those energy states, they have some probability of relaxing and giving off light. And so when we look in our emission spectrum for sodium, we see some colors, or we see some light at a lot of colors in there, but we get these really strong bands at a couple wavelengths. And those wavelengths correspond to the distance between these different energy levels or different orbitals in our sodium metal. So one way that you can get a little more color here, so sodium lamps tend to look really yellow because it has this really strong yellow colored transition between two orbitals. So to give it a little more color, you can throw in mercury. Mercury has a lot more emission lines just because it has a lot more protons and electrons, so it has a lot more orbitals to jump in between, and so you get all these extra colors. So electronic structure matters a lot in the wavelength of light that's being absorbed. So right here, what I have for you is the absorbance spectrum for benzene. On the bottom axis here is the wavelength in nanometers. So this is the wavelength of light. And you can see that this guy is mostly absorbing in the UV region. So below 300 is generally considered UV. And so you'll see that it actually has several peaks, and these peaks each correspond to a different electronic transition. And on the y-axis, of course, I have the absorbance. So the height of this tells you how intensely it absorbs different things. Well, let's change the electronic structure of benzene a little bit by adding a second benzene ring to it. That turns it into naphthalene. And now we have more conjugation here. So it's actually easier for electrons to transition from one state to the other. And so its absorbance spectrum actually gets shifted to higher wavelengths of light, which would correspond to lower frequencies or lower energies of light. And here we actually get more peaks than with benzene, but because they're so close together, it's hard to resolve them. And so it looks more like a big jumbled mess than with benzene, but naphthalene actually has more peaks. We'll give it one more benzene ring and turn it into anthracene, and that will just shift the absorbance a little farther over to the right there. We've talked a little now about how light can interact with matter, but what can that do for us in analytical chemistry? Why do we care when we're analyzing things for concentration and composition? Well, that leads us into Beer's law. So some of you might remember this from a previous class, but Beer's law just relates the absorbance of light to the concentration of your sample. So what all these letters in here stand for, the A, epsilon, B, and C stand for, are listed right here. So A is our absorbance that we're going to get from a spectrophotometer, which I'll talk about in a minute. The epsilon is our molar absorptivity. Molar absorptivity is listed in units of per mole per centimeter. And B is our path length. This is the length of our cuvette that we're putting our sample in. And this will be in centimeters. And for this class, you can generally assume the path length is 1 centimeter unless I specifically say otherwise. So if I forget to put a path length in, just assume it's 1 centimeter. Why do we use our path length in centimeters and divide our molar absorptivity in centimeters? Well, because most of our cuvettes are just 1 centimeter. And of course here our C is our concentration, and that is in molar. All right, so we take our sample, load it into one of these tubes, and then we load it into a spectrophotometer. Here I have just two types of spectrophotometers. This one looks a little more akin to what we have in the lab, though it's not exactly what we have. So a spectrophotometer just quantifies the light being absorbed or transmitted through your sample. And the basic components of a spectrophotometer are: one, you need a light source. So this is the light you're going to shine through your sample. Then two, you'll need a wavelength selector. Why do we need a wavelength selector? Well, it's interesting to see how all light interacts with a sample, but it's more interesting to see how individual wavelengths of light interact. And so we will take our light, shine it through this wavelength selector, and get out individual wavelengths that we can use to interrogate our sample with. Then, of course, we have our sample. Most spectrophotometers use a simple cuvette for this. And we'll talk a little bit more about cuvettes as you go through the labs. So for one lab, we're going to use a plastic cuvette. And the other one, we're going to use a quartz crystal cuvette. The difference there is the plastic and quartz crystal both transmit visible light, but the plastic ones actually absorb UV light. And so you can't see UV light when you're trying to measure at that wavelength for different samples. Then after the sample, we will have our detector. This will just tell us the abundance of light that is hitting the detector. And then finally, we will have our computer. And so what the computer generally measures is the intensity of light, or the information the computer usually gets is the intensity of light the detector is measuring. So there's two basic types of measurements that we're going to want to make with our spectrophotometers. The first is the transmittance of our sample. So the way we measure our transmittance of our sample is, first, we measure our spectrum, our UV-Vis spectrum, for a blank sample, and we look at the power or intensity of that spectrum at every wavelength of light that we can detect. So our transmittance is going to depend on wavelength. So our sample is going to have a different transmittance at 400 nanometers and a different one at 401 nanometers, a different transmittance at 402, etc. So the blank is going to be everything in the sample except for the specific analyte we're looking for. So let's say we're trying to measure the content of iron in stream water. Well, we'll take some stream water, and then we will, for our blank, we'll try and make a sample that's as identical to that stream water as possible, except we'll leave out the iron. So then we'll measure the intensity of that blank spectrum, and then we will measure the intensity of our sample spectrum, and then we will compare those to each other. So transmittance has a limited range of values that it can be. So at the low end, let's say that our sample absorbs all of the light coming through it, so it doesn't let any light transmit through it. Then our intensity of our sample at that wavelength would be 0. So 0 divided by a number would be transmittance of 0. So you can't have less than 0 light transmitted through your sample. It's not sucking light back in from your computer. So the lower bound for your transmittance is 0. And then for the higher bound, let's consider our sample again. And the best case scenario, or the maximum scenario, it's just going to transmit all of the light through. Your sample's never going to be creating additional light, and so your intensity for your sample should never be more than the intensity of your blank. Now, some of you might be thinking, well, what about a glowing sample? Well, that's a good point, but generally if you have a glowing sample, you just put it in the dark for a second and it'll stop glowing. And then when you shine the light through, it actually doesn't glow with any more energy than you put into it. So you're actually not creating more light there. The next value we're going to be interested in is the absorbance. We're interested in the absorbance, of course, because it has a linear dependence on concentration, as we saw in Beer's law. So the absorbance is actually just calculated as the negative log of T. Some of you might be thinking, we do a lot of negative logs in this lab. And you're right. All right, now we're going to go through and talk about each of these components, or at least a few of them, in a little more detail. We're just going to start with the left side of this instrument and work our way through to the right. So we're going to start with light sources. So when you're building your instrument or purchasing your instrument, you want to buy one that has a lamp or a light source with the correct wavelengths of light, so you can investigate the wavelengths you're actually interested in. So we're just going to talk about 3 light sources that cover different portions of the UV vis range. And we're going to start with the deuterium lamp. So the deuterium lamp is just a glass bulb, and it's filled with deuterium gas. So that's heavy hydrogen, or hydrogen with an extra neutron in it. And then it has an electric arc in the middle here that excites the deuterium, and then when the deuterium gets excited, it then emits UV light. So the deuterium lamp is a great source for UV light. If we're looking at the visible range, then we will go with usually a tungsten lamp or a tungsten bulb. So this is very similar to a common light bulb. It just has a metal filament in it that is resistive. And so as you pass electricity through it, it heats that tungsten filament up. The tungsten glows really bright and emits at many wavelengths in the visible region. So this guy literally is almost the exact same thing you have in the kitchen right now, but the only difference is that if you call it a tungsten lamp instead of a light bulb, then you can charge a lot more for it. And then if we want to get into the IR source, or the IR range, we will use what's called a glow bar. So a glow bar is also a resistive material, but it's made out of silicon carbide or other carbides or other silicon compounds. And all this is a double helix. You'll notice this end of this glow bar is divided into 2 pieces, and these 2 pieces coil around each other until they meet up here at the nose. So as you send electricity through this, it heats up and emits light in the infrared region. Since we're just doing UV vis, and our instruments actually are only capable of UV vis, we're just going to use the deuterium and tungsten lamps in our instruments. So your book has a plot of the emission spectrum for both of these guys that looks like this. I've got the wavelength on the x-axis and the light intensity on the y-axis. They've got these drawn as really smooth lines, and they actually have the tungsten lamp going past 700 and 800 nanometers well into the infrared region over here. But this is what the emission spectrum of our lamps actually looks like. So we've got the deuterium lamp over here giving us some UV, and then we've got our tungsten lamp that quickly falls off after 800 nanometers. You'll notice we also have a bunch of sharp peaks. You'll almost always get different peaks and shapes to these emission spectrum depending on the individual lamp that you're using or the elements that you're using. So for example, if a tungsten lamp is made from tungsten diluted with other metals, that'll change the shape of this lamp. And so sometimes you want to do that to get really fine control over the emission shape. All right, so that's your light source. Now let's go on to our wavelength selector. So this is a diagram of our wavelength selector that we use in our experiments. So we have our light source here, and we shine light from that through a tiny slit here. And the purpose of that slit is to make sure all the light is traveling in a single direction. So we don't want light traveling in at weird angles. So really, this is usually kept in a little tunnel. The light comes and hits that slit. Then it comes back and hits a mirror. This mirror focuses all the light onto a diffraction grating. And that diffraction grating will spread out the light and diffuse it so that different wavelengths of light come out at different angles. And that diffraction grating will then send the light to a mirror that hits another slit, which goes onto our detector. You can put your sample actually right after your light source here, and all of the light can travel through at the same time, or you can put it right in front of the detector where you only have a single wavelength of light going through at a time. It actually doesn't make a huge difference. For most samples, the different wavelengths of light are going to have separate effects on your light, so they're not going to overlap or interfere with each other. So it usually doesn't matter whether the sample is right after the light source or right before the detector. But let's talk really fast about this slit right before the detector here and what it does. So this slit, obviously, it filters out different wavelengths of light, so you're just getting through the ones you want. But let's talk a little bit about the width of this slit and what that does, actually. Okay, so if you shine through different wavelengths of light that are really close to each other, so here we've got orange, yellow, and green coming in. If you have a really narrow slit width, you can really finely choose which wavelength of light you're letting through. If you have a broader slit width, then you're going to be letting more wavelengths of light through at the same time. So let's look at some spectra collected with different slit widths. So this top one is collected with a slit width of about 2 nanometers. This one with 1 nanometer, 0.5, 0.3, and 0.1. And these are all collected for the exact same sample, just back to back. And what you'll notice is with the 2 nanometer slit, it just looks like a big blob. Whereas with the 0.1 nanometer, we get this fine structure with 3 different peaks. So why does it look different? Well, because with the 2 nanometer filter, or the 2 nanometer slit width, you're collecting everything from 606 to 608 nanometers and calling that 607 nanometers. So let's say we're looking now at 608 nanometers with that slit width. That's collecting everything from 607 to 609. So it's already collecting this peak over here, even though we're not even anywhere near it. And so it kind of smears out your spectrum like that, makes it all kind of average out with each other. Whereas if you have a really narrow slit width, if you're looking at 608 nanometers, you're actually looking at 607.9 to 608.1, and you're just averaging a much narrower width, and so you can get much higher resolution on those peaks. So why not just go to an infinitely small slit width? Well, the trade-off there, and this plot actually does a really bad job of showing this, but the more narrow your slit width, the lower your intensity on these plots. So the absorbance here, the y-axis is just going to shrink, and your sensitivity is going to go way down, just because you're letting through a lot less light. All right, so that's the slit width. Now let's talk about the diffraction grating and how that works. So diffraction gratings have really tiny gratings on them that are really tiny grooves built in at an angle. And these grooves are roughly have dimensions roughly similar to the wavelength of light. And so what happens is as light comes in and interacts with those grooves, it causes the light to actually diffract in every direction. And so at each of these grooves, you have light diffracting at each direction. But since you have two grooves right next to each other, these grooves are all going to be diffracting light in every direction. And so at certain angles coming off of that grating, you're going to have light from different grooves interacting with each other and having their wavelengths in phase. And if you remember, if you have your wavelengths in phase with each other, they'll add together to get what we call constructive interference, and so it'll look more intense. But at different angles here, what you're going to have is light coming from different grooves being out of phase with each other. And so if you add light that is out of phase with each other, you get what's called destructive interference. And so you actually get zero intensity there. And so what that means is that at different angles, you'll have constructive interference, and at different angles, you'll have destructive interference. And the angles at which that happens is going to change for the different wavelengths of light. And so what you'll get is a rainbow effect where you'll spread out all the light until you get a rainbow that looks like this. All right, now let's talk about our detectors. And this first one is what we call a photomultiplier tube. So the way that this works is as light comes in, it's going to interact with a photocathode. This has a work function that is really low, meaning that it releases electrons really easily when light touches it. And so it's going to release a single electron when this photon hits it, and that electron is going to be pulled through a focusing electrode that has a slightly positive voltage on it. And that electrode's going to come collide with this dynode right here, which is literally just a metal plate with a slightly positive potential on it. And then we're going to have another dynode right here with a slightly higher potential on it. So the electrons that collide here are going to get accelerated down here, and then down here, and then here, and here, and we're just going to ramp the voltage up as we go through this. So we start at about 0 volts, end at about 800 volts. And what's going to happen is as the electrons collide with these different plates, since they're colliding with a lot of energy, they're going to be releasing more electrons than they start with. So this first collision releases some electrons. I'll back up this animation again. Releases some electrons, and each subsequent electron or impact releases more and more electrons. And so this is a cascading effect where we just multiply the number of electrons we have by some factor each time we hit a plate. So photomultiplier tubes are really nice because they're fast and highly sensitive, and you can get about 1 million electrons off of this guy for a single photon, which means that if you have hundreds or millions of photons hitting it, you get really sensitive measurements and get a lot of signal off of this guy. Now this photomultiplier tube actually doesn't care what wavelength of light is hitting it, so you actually don't know from the detector what the wavelength is. You have to know that from the angles of your diffraction grating and mirrors and so forth. So this guy really just measures intensity and not the actual wavelength. Another type of detector that's really common that we actually use in our instruments is what's called a photodiode array. And so this is basically just an array of photomultiplier tubes. And if you have your light spread out in a rainbow, the nice thing about this is you can collect the entire spectrum all at once. So with a photomultiplier tube, you can only measure one wavelength at a time, and the way you choose different wavelengths is you either rotate your diffraction grating or you rotate a mirror so that different wavelengths are hitting the photomultiplier tube at different times. With a photodiode array, and this one only shows a few diodes, in reality these usually have hundreds or thousands of diodes lined up in an array or in a row. You can collect the entire spectrum all at once because the entire spectrum just hits it. So you actually don't have a second slit. You just have that first one in front of the light source. So these are a lot faster than PMTs because you can measure everything at once. But the real bad thing about these, or a limitation I should say, not necessarily a bad thing, is that you can't change your resolution. So the photodiode array's resolution is controlled by the width of each individual diode. So these can get pretty good resolution, but they can't get as good of resolution as a slit in front of a photomultiplier tube, and that is the drawback. But it's not enough of a drawback to stop most people from using them, just because they save a lot of time, and if you don't have moving parts in your instrument, you actually have a lot less parts that can break. So this is an actual diagram of the spectrometers that we use in this lab, where we have a fiber optic leading the light in here, and that light hits a mirror that bounces it onto a diffraction grating that then shines it onto a mirror that hits our sensor, which is a photodiode array. And so we actually have our samples in our experiments coming before the lights or the wavelength selector. All right, so that is fundamentally how a spectrophotometer works. And then this sensor just has some electronic components we won't get into very much that convert that signal or the current of electrons flowing off of that into something a computer can read. But that is fundamentally how a spectrophotometer works. All right, let's do some practice now with some data and see what data actually looks like and how we're going to manipulate it to get meaningful values for the next couple of labs. All right, so first what we're going to do is we're going to prepare a blank, and we're going to run that blank through our spectrophotometer. It's going to give us a spectrum that looks like this, with the wavelength on the x-axis and our intensity of light on the y-axis. Okay, then we're going to take our sample, run it right after that. And our sample, you can see its spectrum here is this orange guy. We're going to take these two data then, or these two spectra, and compare them to convert into our absorbance. So what I'm doing here is at each wavelength of light, I'm taking the negative log of the intensity of our sample, dividing it by the intensity of our blank. So you can see the sample and blank have almost identical spectra out here beyond about 300 nanometers. And so that means that the sample is not absorbing at all in that region. But you'll notice that these do look fairly different between 200 and 300 nanometers, and that means that we're actually getting some absorbance by our sample in that region. So now that we've gone from our raw data to our absorbance data, let's practice with that absorbance data. I'm going to zoom in on this 200 to 300 nanometer range here. Okay, and we're going to look primarily at 228 nanometers because that's the place with the highest absorbance, at least on a peak that we can fully see. Okay, for this problem, or I'm going to actually give you two problems here. We're going to assume a path length of 1 centimeter, and we're going to assume the absorbance here is 1.73. All right, now these two are two separate problems, so they're not related at all. They are both using these data, but all of this data is just made up, or at least heavily edited from real data. So don't worry too much about whether these two questions correlate. All right, with all that intro, if the epsilon, or the molar absorptivity at 228 nanometers is 122.3 per mole centimeters, what is the concentration of the solution? And the second question is, if the concentration is 0.107 molar, what is the molar absorptivity of the solution? All right, you have Beer's law here. You have all the information you need to answer these two questions. So go ahead and pause the video and try and work through both of them. All right, the way you should work through this first problem is we're looking for the concentration. So we're just going to take Beer's law here and solve for concentration. So our concentration is just going to be equal to our absorbance divided by our molar absorptivity and our path length. So we have our absorbance of 1.73, our path length is just going to be 1, and we have our molar absorptivity up here. So we're just going to plug that all into our calculator and get this value of 0.0142 molar. All right, so the next question now, we're going to start with a different concentration. This has a concentration of 0.107 molar. And since we're starting with a different concentration but the same absorbance, we should get a different molar absorptivity. So all we're going to do here is solve this equation, Beer's law, for molar absorptivity. So that's going to give us our absorptivity divided by our path length and concentration. We're just going to plug that into our calculator and get a value of 16.2 per molar centimeters. All right, if you got those wrong, try and figure out why you got them wrong. If you didn't practice them at all, shame on you. Do it anyways. All right, and if you have other problems with it, let me know. All right, now let's back up a little bit, and instead of giving you the absorbance data, what if I just give you the intensity of these spectra between 200 and 300 nanometers and asked you some questions about this? All right, so let's still stick at 228 nanometers, but let's say that the intensity for our blank was 1084 and our intensity for our sample was 558. By the way, if you're wondering what units this intensity is in, it's actually in arbitrary units. So this really just depends on what voltage we're applying to our photodiode array. If we turn up the voltage on it, that will increase the intensity here without actually changing anything about our sample. And if we turn down the voltage, we'll decrease the intensity, etc. So this is just arbitrary units over here. But now we have our intensity of our blank and our intensity of our sample. And I'm going to tell you that we're dealing with a sample that has a concentration of 0.0510 molar. I'm going to ask you, what is the molar absorptivity of the analyte? So can you take all of this data and turn it into a molar absorptivity? Go ahead and pause the video now and see if you can work through that. And I will walk you through it here in a second. All right, so here is how you do it. First, you're going to want to find your absorptivity. You might think that first you want to find your transmittance, and you can do that too if you'd like. I prefer to calculate my transmittance and absorptivity all in a single equation. So here I have the negative log of the intensity of the sample divided by the intensity of the blank. And of course, this stuff in parentheses right here is our transmittance. So we'll take the negative log of that transmittance, and that will give us an absorption of 0.2884. We will then take that and plug it into Beer's law, and we will solve Beer's law for the molar absorptivity here, which is epsilon. So epsilon is equal to A over BC. And once we plug in all of our values here, so we plug in our value for A of 0.2884 here, and for A, we plug 0.0510 in for C. It didn't give you a B, so we're just going to assume that it is a path length of 1 centimeter, and that will give us a value of 5.65 per molar centimeters. All right, make sure you understand that well, and you can follow all of that logic. One last thing we're going to cover today is what's called signal-to-noise ratio. So this is actually a principle that's useful in all analytical measurements, not just UV vis, but this is a good place to introduce it. I'm actually going to introduce it not using UV vis data, but using mass spectrometry data. So this is data that I collected in graduate school. And what you can see is on these top two spectra, we're not going to worry too much about what the data is. These are actually just measurements of cytochrome C, which is a protein. And on the x-axis, we have a mass-to-charge ratio, and on the y-axis, we have just relative intensity of these peaks. But what I want to draw your attention to is in these top two spectrum, we have these sharp lines and then nothing really on the baseline. The baseline here looks really clean. But on this bottom spectrum, we have all this black fuzziness all the way across. This black fuzziness is just instrumental noise, as are each of these peaks with an apostrophe above them. And so what you can see is there's almost no noise, or you can't really even see the noise in these top two spectra, but in these in this bottom one, you have quite a bit. And so if you look, for example, at this peak that I have labeled as 10 plus with a green triangle, that peak is less intense than several of these noise peaks. In fact, the most intense peak here is an instrumental noise peak. So how then do we know if what we're seeing is noise or sample? Well, we quantify how well we can see a peak using this signal to noise ratio. And so all this is you take the intensity of your signal and you divide it by the intensity of your noise. So for example, this 15 plus peak has a signal intensity of about 100% and it has a noise intensity of about 10% around it. So it has a signal to noise ratio of about 10. The way we were able to claim this 10 plus peak here was real, even though there were other peaks around it, is because the noise around the 10 plus peak was fairly constant. And if you remove this sample and just look at the noise is a little below that. So every time we put the sample in, we'd get a little peak there. All right, so that's enough about this data specifically. Now I'm going to talk about some general signal to noise rules. So the first one is, if you have a signal to noise ratio of 1, you can't say that you're actually detecting something, because a signal to noise ratio of 1 means that your signal is exactly as high as your noise. So if you can't tell the difference between your signal and your noise, you can't tell that you have any signal. If you have a signal to noise ratio of about 2 to 3 or higher, that's generally what's required to identify something as being there. You have to have that value to say that a peak is real. I'm probably cutting it pretty close on this 10 plus. I'm probably even violating that rule, but if you're a physics person, you're actually fine with doing a lot less. They found the Higgs boson with way less than a signal to noise ratio of 2. So there's some people that are still a little skeptical about that data, including myself. Not saying the Higgs boson isn't real, just saying they did a very bad job of detecting it if it is real. All right, now next thing is, if you want to quantify something, you generally have to have a signal to noise ratio of 10 or more. And so what this means is, if you have a signal to noise ratio of 10, so for example with this 15 plus peak that we saw, that means you have a signal of 10 and a noise of 1, and that noise is all included in your uncertainty. So you have an uncertainty, or a relative uncertainty, of about 10% there. And so where do these numbers of 2 or 3 and signal to noise ratio of 10 come from? Well, these are mostly by convention. So these are numbers that people in the scientific community have generally agreed to adopt. There's not really any scientific reason for this hard cutoff at a signal to noise ratio of 10, but it's generally what people require. If, for example, you're dealing with a precious sample where you can't make more than one measurement and you can't get a signal to noise ratio of greater than 10, usually you'll just report that and explain why you can't get that good of a signal to noise ratio in your publication. And so everyone can take that information for what it's worth, a data point with a large amount of uncertainty, which can still be valuable in a lot of cases. All right, so now let's bring this back though to UV-Vis and talk about the signal to noise ratio in our UV-Vis spectra. So in the absorbance spectrum of a single sample, you might get something that looks like this, but the noise in our UV-Vis experiment is actually constant across this whole spectrum. So how does the noise or signal to noise ratio change as you move across this? Well, it's going to be pretty low over here where you're getting no absorbance. You'll get a signal to noise ratio of 1 where these two lines cross. And you'll get the best signal to noise ratio at this highest peak. And so since that's where you get the best signal to noise, that's generally where you get the least amount of uncertainty in your measurement. And so that's generally where you're going to try and take your measurement. So you're always going to try and use your most abundant wavelength. So when we look at our absorbance here versus the percent standard deviation we get from our measurements, you'll notice that we get really high uncertainty when we have low absorbance, and we get some more uncertainty when we get high absorbance as well. So why that is because when we have no absorbance, what we're comparing is the signal intensity from two samples. And if you're not looking yet, go ahead and look at my picture where I'm wiggling my fingers. Each absorbance spectrum is going to have some uncertainty associated with that, some electronic noise. It's going to kind of look like wiggling. And if those two lines or those two spectra are far apart, the uncertainty is not contributing a ton to that difference in between these, right? But if we're comparing a difference that's really small like this, and we still got a bunch of wiggling noise in there, that's going to give us quite a bit of noise when we have low absorbance. Now, why then do we get this higher noise when we have higher absorbance? Well, in this range, so we're still comparing this intensity of our sample to our blank, but now the intensity of our light making it through our sample is just so low that it's hard to detect. And so we get a lot more uncertainty in that region. So for our instruments specifically, we're going to be shooting for an absorbance of between 0.3 and 2. And that again is just for our instruments. Other instruments can get a little bit better sensitivity or a little bit better dynamic range. Some other notes that you'll want to notice for making measurements with UV vis, especially when dealing with cuvettes, you're going to want to not touch your cuvette with your fingers where the light is traveling through, so you want to minimize fingerprints. And you also want to deliberately place the cuvette every time. Try and position it in the same corner of the cuvette holder every time so that the light's traveling through the same path each time. We'll finish that off with a magical unicorn. I know at the beginning of the lecture I said I would have no unicorns, but guess what? That was a lie. I've tried to find a soundbite of a unicorn saying believe in your dreams, but I haven't found that yet. Someday I will, and that is my dream.